Peter, for inviting me over. I'm from the Department of Biomedical Engineering at Tel Aviv University. My name is Amir Geffen, and I'm, as Antida mentioned, an engineer. So I'll give you kind of a different perspective. I'm a mechanical engineer by background, with a master's and a PhD in biomedical engineering. And what I'm interested in is mechanobiology. And I'm looking at mechanobiology in different aspects, for example, in the aspect of wound healing, tissue regeneration, but also in the aspect of how cells generally function under mechanical loads, and how do mechanical loads affect normal function, and how can mechanical load introduce abnormalities in function of cells and tissues. And today I'd like to focus on the mechanobiology of a very poorly studied type of cells, which is fat cells, adipocytes. And it's quite surprising that they're so poorly studied, because they're so well connected to the most important epidemics of the developing and developed worlds, which are obviously what we call diabesity today, which is the combination of obesity, overweight and obesity, and diabetes. They very typically go together, these two diseases. And that's a nice image here from the cover of Science from a couple of years ago, showing fat cells. These little balls are fat cells, and they're held together by connective tissue components, by collagen mainly. But unlike other tissues, in fat, most of the volume of the tissue is the cells. So for example, if you think of other tissues like cartilage, most of the volume of the tissue is extracellular matrix. In fat, most of the volume of the tissue is the actual cells. Moreover, within the cells, when you look into the structure of individual cells, most of the volume of the cell is fat, triglycerides. And basically, these cells start their life cycle as cells that are very similar to fibroblasts. We call them fibroblast-like pre-adipocytes. And they look very similar to fibroblasts. Actually, you can't really tell if you don't know. You can't really tell the difference. They're elongated, and they're motile. And at some point, when they differentiate, and I'll speak about it later more, they start to develop these lipid droplets that grow bigger and bigger and merge together, and basically inflate the cells until they are so big that they are bigger than the nucleus of the cell. Basically, the cells, the individual cells are getting fat. That's what happens. And they also start pushing against each other. It's a very packed organization of the tissue. Some other things that I should mention is that fat tissue is much more than just an energy storage machine. People think of it as kind of an energy storage depot, but it's more than that. It's an organ. It's a whole organ with a series of functions. It releases hormones, for example, that affect, for example, hunger, how hungry we feel. No, not angry. Well, sometimes angry too, but mostly hungry. It's highly vascularized. A lot of blood vessels, a lot of capillaries in it. Very dynamic, metabolically, very dynamic.
A question?
Yes,
You
sure.
said these cells are big. What's the length scale?
Couples of tens of microns to 100 microns. Yeah, big. This is a three-dimensional reconstruction of cells from a culture that we have made based on confocal microscopy, and what you can see here is basically the lipid droplets in the cells. And what we do, which is something that I often do with my research, is to look at the function of fat tissues and cells in a multi-scale approach. So we look at how, for example, because I'm a simple mechanical engineer, not a smart mathematician like you, I'm focusing on structures and how structures, their mechanical loads, and these structures can be looked at different scales. For example, you can think of the buttocks, well, you're all sitting now, you can think of your fat tissue, you have a lot of fat tissue enveloping the gluteus muscles in the buttocks, and that fat tissue is now being deformed as you're sitting and listening to me. And within that fat tissue, if you can zoom in, these individual cells, these adipocytes, are also deforming, and the organelles within the cells are also deforming as you're applying these sustained deformations on the buttocks, these sustained loads on them. So all these little organelles here, the cytoskeleton, the plasma membrane, the lipid droplets, the nucleus, they're all experiencing deformations, and we look at all these different layers of the hierarchical problem to understand how fat tissue functions, first of all mechanically and then biomechanically. And we start with the cell level. And again, the medical relevance of all of this work is overweight, obesity, and the balance between muscle and fat tissue, which is a problem that is, I think, of interest to all of us. The simple question that you can ask is, okay, how do we gain fat mass? How do we become overweight? That can happen in two different ways. First of all, you can have more of the same. You can have more cells, right? And that requires proliferation. But the thing is that after these cells have acquired the adipocyte phenotype and started to produce these lipid droplets, they can't divide anymore. They can't proliferate. They can only divide at the pre-adipocyte fibroblast-like stage, okay? So pre-adipocytes can divide and become adipocytes later on in their life cycle. The other thing that can happen is that each individual committed adipocyte can increase in mass through synthesis of fat, of triglycerides, which is what they contain mostly. So as I said, they increase in volume and mass. So that's another mechanism. So you can have more of the same, or you can have bigger ones. And in the body, in the human body, what happens essentially is both, right? They both proliferate and become adipocytes and grow bigger as they mature. So you really need to watch these cells to understand how they function. And sometimes we are just living a culture in a mini incubator in the lab and putting the camera on and just trace them, just watch them. And these are cultured cells, and you can see that they don't have one huge lipid droplet, they have multiple. And that's something that you typically see in cell cultures, as opposed to histology, because in a physiological system, in the human body, all these droplets merge together to a big one. Whereas in cultures, you normally don't see that. Sometimes you see that, but it's difficult to get that. And let's try to see if this will work. Works on my computer, but it's frozen on the screen. to show you is that these lipid droplets, first of all, you can clearly see that they inflate the cell. Not only that they inflate the cell, they produce forces on neighboring lipid droplets and form the wall of the cell, the plasma membrane. So as the cells develop these lipid droplets, they also develop internal mechanical loads. Not only that they develop internal mechanical loads, they're also acting loads upon each other. Because suppose that I'm a cell which is now less differentiated, like this guy here, which is neighboring a cell that is more differentiated and that has produced more lipid droplets, like this one here, what I will feel is that basically that my neighbor is pushing me. So from a mechanical point of view, these cells not only act forces, not only generate forces internally, but they also act forces upon each other.
A question?
Yes.
What are they taking up during growth? I mean, is it because there's high glucose in the bloodstream?
Yeah, that's basically what they do. They synthesize, they uptake glucose and synthesize through a complex molecular process that I'm not going to get into. They synthesize these triglycerides from the glucose. So that's their food, basically. You can also see that, work now. You can also see the process of merging of small droplets into bigger ones. If you look at these small droplets that are forming here, you can see that they're kind of being swallowed by the big one, right? So, and that's basically the dynamics of the process. First of all, there are some foci of like nucleation spots of lipid droplets. And then once these lipid droplets are touching each other, they tend to merge, and then they grow bigger. So typically you would see that there are many lipid droplets in the beginning, but then as you monitor their number, and I'll show you in a minute how we do that, as you monitor their number is first of all increasing and then decreasing because of the merging, but at the same time they're getting bigger.
So they don't have membranes. They're not membranated vesicles.
They do have very, very delicate membranes that envelop them. So they do have membranes and they still merge. How is that happening? Not exactly clear, but they do have membranes.
Question.
Yes.
Do you observe adhesion forces between two cells?
Let me get into that. And this, what you see here, by the way, is 24 hours. 24 hours in the life of these cells. Okay. That's not my bread and butter. I also work with molecular biologists and cell biologists. But the bottom line of this slide, which is obviously describing signaling cascades, is that fat cells, adipocytes, are mechanosensitive, and you can trigger or suppress adipogenesis by interfering with these signaling cascades. And these signaling cascades can be activated by either static stretching or dynamic deformations, like cyclic deformations. And what we have shown is that once you apply static deformations, and I'll get into the details of that, you can actually enhance the adipogenesis, the production of these lipid droplets. And there is also some evidence in the literature, mostly coming from Japan, showing that as you apply cyclic deformations, you kind of inhibit the adipogenesis process. And these signaling cascades, at least their fundamental components, have been identified recently. Yes.
Does this also mean that if you have these cells,
are actually expanding, adipocytes that are expanding by the uptake of lipids. At a certain moment, they start pushing on their neighbors.
Yeah.
And I guess that's a very static law, isn't it? So you get something like a chain reaction by that.
Yes, yes, and that's basically, you've just summarized the talk.
Oh, sorry.
But that's the point that I'd like to make in this talk. And so the whole thing, I need to tell you a little bit of a background. The whole research concept came from my work in chronic wounds. I've mentioned that I'm interested in chronic wounds, and I use a lot of MRI. And some of the MRI data that we're looking at comes from people with a spinal cord injury. And people with a spinal cord injury tend to experience disuse-related changes in their tissues. For example, muscle atrophy, they lose muscle mass very quickly, and this is very well characterized in the literature. But what we've noticed with these MRIs is that muscle tissue doesn't just go away and vanishes. It is basically being taken over by fat. And that happens both externally from the fat of the buttocks that I've mentioned already, but most interestingly, it also comes from within the muscle. You've all seen steaks, I guess. And a good steak is a steak with pieces of like marbles of fat in it. This is the intramuscular fat. And we all have intramuscular fat. That's normal. That's an immediate, again, energy depot for the muscle. But what happens when the muscles are being atrophied, which can happen if you lie on a bed for long periods, or if you're if you have a spinal cord injury, or if you fly to space. What happens is that these fat depots in the muscle, the intramuscular fat, expands and expands and expands on the account of the muscle. And we've seen that happening in these MRI images, these MRI scans, and we thought that we want to reproduce that in a lab setting, looking at the individual cell level. So we've built some of these, what we call cell torturing devices, cell stretching devices. And they're based on the Flexcell 6-well plates with an elastic substrata, with an elastic bottom. But we've developed very simple frames to mount these plates on that allows static stretching of this substrata.
Excuse me.
Yes.
Is there a lower setting on your laser pointer?
Why is
I'd like to look at your slides, but
Oh,
I'm
sorry,
being
that's
blinded
no,
by
that's
You
made
have
in
another
China.
pointer.
That's what they do.
You have another laser pointer.
Okay.
Is there a device which should switch the slides on and off? I have one.
Here?
Yes, yes. In the middle.
Here, try this
I
one.
just couldn't take it anymore.
Or stick.
The on switch is to the left hand, on the left hand side. On the left hand side is the on switch. To come on, you press it.
This one? Oh, okay. It's so
Is that
small that I
acceptable?
couldn't see it.
Your eyes are closed.
Okay, so so these are the elastic substrata, and the cells are cultured on the top of the substrata, and something is pushing from the bottom, and you can control the extent of that pushing. So essentially, it's like a balloon that you stick your finger onto, and essentially this is stretched, and the cells which are attached are stretched with it. And we've developed some image processing codes that basically allow the quantification of the sizes and numbers of the lipid droplets per field of view or for individual cells from simple phase contrast microscopy. So there is absolutely no chemical staining here of any kind. You basically take the culture from the incubator, you put it under the microscope while it is being stretched. You take the images, you put it back in the incubator, you come the next day, you do the same, and then you basically have ongoing monitoring of the production of the lipid droplets in the cultures for weeks, because it takes these cells weeks to produce these lipid droplets. And since you don't stain the cells, it's statistically very powerful, because you look at the same culture every day. Yeah.
They are dividing,
Sorry?
the cell dividing.
So I mentioned that they only divide
Up
at the pre-adipocyte,
Okay.
but once they start doing this, they can't divide anymore. They also can't move anymore.
Okay.
They can't do anything. They just sit on the couch and get fat.
But is it the ECM that is exerting the stress on the cells? Because an individual.
There's no real ECM here because these are cultured cells in the monolayer, so the only thing that they see around them is media.
So what's keeping them on the top there as you stress it?
Oh, so they're cultured on these on this elastic sheet here.
Right.
So they on the bottom they are attached to the sheet, and the superior surface is free basically.
So that's where they get the stress from.
And that's also where they get the nutrition from. And okay, so this is the actual data. As days go by, you can see that there is more lipid per field of view, and you can see what I've mentioned previously, that the number of lipid droplets is increasing and then decreasing, and the size is constantly increasing, the size of the lipid droplets. That's all is not a big surprise, but the surprise was that when you apply these deformations, basically radially stretching the cells, and these deformations exceed a certain threshold, say about 6 to 9% strain, which is totally physiological because fat tissue experiences much more than that. Even now when you're sitting, it's tens of %. You see that a difference is, even without the quantification, a difference is apparent in the behavior of the cell. And that difference appears at about 3 weeks after the cells started to differentiate, where you see that the cells that have been subjected to large deformations start accelerating their adipogenesis substantially, I would say even 50% more. And then the question is obviously why and how they do that. First of all, we wanted to understand structurally how the cell is changing when lipid droplets develop. First of all, as you've seen already from the movies, the cell is becoming very packed, very dense internally, because these lipid droplets start to basically occupy all the space. And so we have used atomic force microscopy, and we looked at individual cells, and we've put a probe of the microscope just above the nucleus, or just above a lipid droplet, or just above nothing, and tried to measure the differences. And we also simulated the experiments by means of finite element modeling to make sure that everything makes sense. But the bottom line is that, as you could expect, the cytosol is very, very soft. The nucleus is the most stiff component in the cell, and that's all known. But the lipid droplets are somewhere in between, actually closer to the nucleus in terms of the stiffness than to the cytosol. That means basically, since you have more of a stiff component, and that stiff component is constantly growing in size and volume, that the cell effectively is not only becoming bigger, it's also becoming stiffer. So again, going back to my example of the two neighboring cells, now if my neighbor used to be a really soft, nice cushion, now he became a steel ball. And that steel ball is poking me, pushing against me. Now reminding you that these molecular signaling mechanisms are triggered by deformations, either cyclic or sustained. So essentially a neighboring cell would induce, besides of all the internal deformations, a neighboring cell was actually, as Fred said, because Fred understands things very, very fast, a neighboring cell would basically deform the plasma membrane and that deformation will grow bigger and bigger as that cell differentiate. So not only his own plasma membrane, but also the neighbors.
Are you sure that you're getting the stiffness of the droplets or the effective stiffness due to stretching the cytoskeleton around this?
Well, what happens in these cells, and you could have probably seen that in the movies, is
I
that
was blinded,
what?
but I couldn't look at it. I was blinded.
No, but I've changed the point of it. So for the fragments that you could look at, you've probably seen that as the cells become dense and the lipid droplets are occupying a lot of the volume, something needs to happen to the cytoskeleton, right? So the cytoskeleton doesn't stay the same, it remodels, it adapts, as it always happens with cells. And so, and I don't have the staining for that here, but what happens is that these lipid droplets basically push the cytoskeleton to the periphery of the cell. So there's almost no cytoskeleton, and that's why they're not mobile as well. That's why they can't move. It's really almost like a person who's getting fat on a couch. They lose the muscles because all the actin is pushed away to the periphery of the cell, so they can't contract. And basically, we can quite safely say that once we poke at around the center of the cell, that's lipid droplets that is under the probe.
Has anyone quantified how much actin and myosin there is? Because typically cells have a cortical layer that helps maintain their shape.
Well, these are all questions that we're dealing with now. It's all very new, these things. I told you, these are very poorly studied cells, surprisingly.
Despite how many there are in the world.
Yeah.
How many problems we want to do?
So just to make sure that we're looking at the right thing, we used, in terms of stiffness, just to make sure that basically that these lipid droplets are stiffer than the cytosol. We've used another method just to verify the AFM, although AFM is kind of gold standard. So we used a microscopy method, which is called wide field interferometric phase microscopy, which basically shows fluctuations of organelles in the cell. So what you're looking at here in these movies is fluctuations of lipid droplets. And what these movies essentially say is that these lipid droplets are kind of turning. You could also see that in the movie of the culture. These lipid droplets are also a little bit, first of all, they move and they're turning a little bit due to, you could say, thermal fluctuations or something like that. And the fact that they are turning within a liquid, within the cytosol, means that they're stiffer than the cytosol. So this is just a verification to make sure that the AFM provided at least trends, accurate trends of effects. And these are finite element simulations of idealized cells. So we kind of gave them kind of a round projected area, but the structures of the lipid droplets and the nucleus are quite accurately represented here. And this is just to show that as the cell develops these many lipid droplets, and these lipid droplets grow, effectively it becomes stiffer. So it could be intuitive from what I've said so far, but we wanted to also quantify it by means of finite element modeling. So it's clearly stiffer because it contains all these stiffer elements. It's clearly stiffer either in compression or in stretch.
Stiffer, you mean dynamically?
Stiffer when
temporarily.
stiffer when someone is or something is applying external.
Strain stiffening.
Yes, yeah. When it's subjected to external loading. Another method that we're using to understand how these cells behave is traction force microscopy, and this is a collaboration with Professor Daphne Weiss from the Technion. And in the traction force microscopy system that she has at the Technion, we're basically culturing these cells and look at how they change their patterns of force application on elastic substrata, like the elastic substrata that we use to stimulate them mechanically, how they apply forces on substrata as they mature and start to develop these lipid droplets. And you can see what I told you. This is the pre-adipocyte stage, a fibroblast-like elongated cell, looks like a fibroblast, and like a fibroblast applies its forces in two poles on the surface, whereas as they mature, the forces on the surface tend to become a little bit more uniformly spreaded along the periphery, along the boundaries of the projected area of the cell.
Are these focal adhesions or less specific adhesions?
These are probably focal adhesions, yes. And you could also, from traction force microscopy, you can also extract some interesting measures. For example, you can look at how the total traction force relates to the projected cell area. Now, there's a large scatter here, but remember it's biology. You do see a trend where the more mature cells obviously are bigger, but you do see a trend if you look at the ratio between the total traction force and the projected cell area. You could say that there is some, at least as a guide to the eye, there is some proportionality here. So it's kind of a stress that these cells are applying, which is a force over the area, that it kind of, I don't want to say stays the same, but that's the word which comes to my mind now, stays the same, because there is probably a capacity of the molecular motors of the cells that these cells can exceed, much like in a muscle. You have this stress limit, this physiology of stress limit. So the stress, even though they grow bigger, they can't produce more stress on the environment. We also look at how the shape, the morphology of the cell, which evolves obviously as the cells differentiate, is related to the total traction forces. And you can see that for very eccentric cells, which are clearly the pre-adipocytes, which are elongated, and so their eccentricity is close to 1. For these cells, the traction forces are very scattered, so there's a very wide range. And as these cells become more round, so they increase in circularity, like you see here, or decrease in eccentricity, these two things relate, of course, the forces are reducing. So there is kind of a relationship between the morphology and the force production. Now, this was all at the cell level, at the level of individual cultured cells. I want to go up the hierarchy here to the meso level to look at interactions between cells. For that, we're using, again, different model systems. We like to do tissue engineering work, and tissue engineering is an ideal, I would say, research approach to look at how cells interact in 3 dimensions. So we have basically developed models of obesity in a tissue engineered model system, where we basically see these cells in hydrogels and stimulate them biochemically to differentiate, and see these. We see again these lipid droplets forming in the cells. This is basically tissue engineered fat. It's not yellow, it's red, but this is just because of the color of the medium that we are using. But there are fat cells in it. And what I want to actually show you is a finite element simulation of loading experiments that we've conducted on these tissue engineered fat. And I'm showing you the finite element and not the actual experimental data, because the finite element, I think, visualizes more nicely what we are observing, which is that once you apply external loads to these constructs, and I've shown you already that the more mature cells are stiffer because they contain a lot of lipid droplets, and these lipid droplets are stiffer. as any structure, loads will tend to go through the stiffer elements in the structure, right? So, you know, that's the reason why they reinforce concrete with steel, with metal bars, because these metal bars attract the loads, so the loads tend to go to the metal bars, which are stiffer. So obviously the same thing will happen here. The external loads, and you can see that, will tend to transfer along paths of the stiffer elements in the structure, which are the more mature cells. Now, what happens if I'm, say, a less mature cell, like this guy here, right, which is happening to be on the road, on the way of these load transfer paths that are coming from the more mature cells, which are focusing these loads. Well, this poor guy, just because of the, you know, selecting the wrong neighbors, he'll be, you know, like these, again, the cushion and the steel ball, he'll be pushed or loaded by his neighbors. And specifically, the plasma membrane of this cell will be locally deformed in a sustained manner as a result of being in proximity with these stiffer cells. And that basically points to what you said, Fred. And we've also developed, and that's just nice from, I would say, a research point of view, because the concept is very clear already, I think. We have developed also three-dimensional models to represent our three-dimensional tissue engineering work. And these models are stochastic in the sense that you have, well, you have these bulk of finite element mesh of an extracellular matrix. Here there's an actual extracellular matrix. And within this bulk, the code seeds cells at different maturation stages and with different internal architectures. For example, just a few or many lipid droplets at different sizes, with the nucleus being in different locations, basically to represent both the biological variability and the variability that we are observing within cultures, either two-dimensional or three-dimensional. And then again, you can look at interactions between cells, and each of these cells in the modeling contains all the elements that a fat cell has: the nucleus, the lipid droplets, the plasma membrane. So it's a real multi-scale model. And you can look at the interaction between cells for different cell populations, incorporating cells at different stages of maturation. And without going into the details of the technical details of the modeling, it's not surprising that, again, once your neighbors are more mature, you are more deformed, because your neighbors are bigger and stiffer. That's as simple as that.
But the stresses here are being transmitted through the hydrogel.
Yes. Yeah. And that's, I would say, a little bit more physiological than what I've seen, than what I've shown with the monolayer cultures, right? Because here it's all three-dimensional. The cells are round, or almost round, which is what the shape that they're getting in spherical, the shape that they're getting in native tissue. And the interactions are three-dimensional, coming from all directions. And you can see that these plasma membranes are being stretched both because of the internal formation of lipid droplets and because of the neighbors. So you could basically schematically describe the processes here at the cell scale and at the mesoscale with these following components. First of all, there is differentiation, and the differentiation, which means that there are more lipid droplets, and the lipid droplets growing bigger, increases the cell stiffness, and that increases the tensile strains or the stressors in the plasma membrane and the inhomogeneity in the tensile strains, and that also reflects to neighboring cells. Now, going to the body level, we're also, again, trying to generalize our multi-scale approach from the whole body to the individual cell. And I told you that I like to play with MRIs. So this is just a wooden stage that we've built to scan the buttocks of a lying individual in basically deformed and undeformed configurations. And so basically we have two scans and we get the undeformed configuration, and then we can basically load the finite element model and see that we actually get the deformed configuration in the finite element model that we got in the real experiment. So we know that everything is deforming internally, including the fat tissue. Everything is deforming internally as it should have been in reality. And then we ran these simulations, and we know the continuum scale or the continuum range of tissue deformations and strains. And obviously you could do the same in sitting or in any other position. And then we go back to the cell level, and again, looking at different compositions of fat tissue, different levels of differentiation. We look at the cells and the loads that are transferred to the plasma membranes of the individual cells at different locations in the buttocks, up to the level or down to the level of segments of the plasma membrane of the cell in the simulation. And then what we do is we introduce pathologies or pathophysiologies into the model. This is the fat infiltration that I've mentioned. This is not normal. This is spinal cord injury related atrophy. You can see that there is not only a lot of extramuscular fat, there's also intramuscular fat at quantities that are abnormal. You can see how thick this fat tissue is here within the muscle. And we can three-dimensionally represent that. These things that look like little worms here are basically intramuscular fat. And this is really important to understand the mechanical conditions to which these intramuscular fat is exposed to, because this intramuscular fat contains an important component of mesenchymal stem cells. And from these mesenchymal stem cells come the muscle tissue, the bone tissue, and the fat. So basically these mesenchymal stem cells can have either fate, and this fate is predominantly determined by the mechanical loading environment. So if there will be a static loading environment that is being sensed by these mesenchymal stem cells here in the intramuscular fat, they will tend to not only select the adipocyte phenotype as their fate, but to also accelerate the adipogenesis, as we've shown in cell cultures. It's a chain reaction, exactly.
We should keep on running.
We should definitely keep on running and don't sit by your computer for too long. I think that I've kind of described the whole process from the cell scale to the body scale, at least the essentials. As you can imagine, this line of research made a lot of headlines in the international media, because it basically concerns anyone. It started from our, as I've said, research on spinal cord injury, but it generalizes to sedentary lifestyle and what a sedentary lifestyle can do to the mechanobiology of fat or fat versus skeletal muscle tissues. And that's something that concerns everyone, especially people like us who tend to sit all day. And I'll leave some time for, I don't know, if not coffee, then just a little bit of a break before Fred's talk, just to thank all the many students that I had that had and have were doing this work, and my collaborators in cell mechanics and microscopy and optics and cell biology. It takes a lot of expertise to do this research. And obviously funding, you can't do anything without money. And thank you for listening. And again, thanks for the invitation to come and speak here.
Questions? Any questions? Yeah, Stefan?
Did you look at the process of merging between the droplet inside the cell? Or?
No, not really. We've just observed it, but we didn't look into the. Well, maybe I should say that we did develop a very initial model, Fred and I, a couple of years ago, based on the Cahn-Iliad equations. And Fred can explain it better than I can, but it's kind of a simplistic way to describe the formation and the merging of the droplets based on concentration gradients.
And so you say they are moving this droplet, do you know how?
Probably a combination of cytoskeletal activity and something like Brownian motion, I think, or thermal motion that takes on there because of the metabolic activity that these cells are metabolically very active. It's a little factory.
Could it also be like the motion of the cytosol inside?
Well, that relates to if there is for example, contractions in the cytoskeleton, then that flows the cytosol fluid.
Sure.
Related, you observe the merging, but did you observe the fragmentation of the droplet?
No, not really.
So to take it completely out of the scientific realm, but into the public policy.
Mm-hmm.
So where do you see this kind of thing affecting how we should treat obesity or something like that, other than the obvious fact, get off your butt?
First of all, if you look at my papers, and we published last 4 or 5 years, we published a lot of them. Then the thing that I'm always starting with is that for some reason, obesity and diabetes as well are seen as metabolic diseases. Obesity is, in particular, is being looked at in a very simplistic way. I mean, how many calories you consume, how many calories you burn, daily activity, physical exercise, nutrition. That's the science of obesity. And they've never been perceived as a biomechanical or mechanobiological diseases. Now, maybe I look young, but I'm old enough to remember that cancer, for example, no one has thought of cancer. Like 15 years ago when I worked in the States, I worked with someone who was, she was claiming that cancer is a biomechanical disease. Because at the cell level, there are so many changes that take place. You know, how do you diagnose breast cancer? You probe it, and you feel that something is stiff there. At the cell level, this stiffening means a lot. And at the time, she was a pioneer, but now everyone is doing work on the difference between the mechanical properties of cancer cells as opposed to non-cancer cells. So cancer is now, it's a consensus, it became a consensus that cancer is a biomechanical disease, or a disease that has a lot of biomechanics into it, right? What I'm trying to say is that I think this is first of all, this is that's one leg is in the scientific arena, and the other leg is in the public policy. That obesity needs to be perceived as a disease which is much more complex than just a balance of calories. That's my first point. The second point is, once you understand that at the level of regulatory bodies and even the public, once you understand that, there are all sorts of things that you can do to manipulate the mechanical environment of the cells so that they stop doing what they're doing. We had this conversation yesterday about gyms, and you know that there used to be these vibrating belts, like 20 years ago. It used to be a very popular thing. Huh? 100 years ago. Well, Going back to that, I do believe that there's something in it. Maybe the frequency isn't right, maybe the magnitudes aren't right, and you need, and that's basically what we're trying to understand is what kind of frequencies and magnitudes is still love or hate, right? But then you can design everything from chairs to gym equipment that is tailored to make these cells suffer, essentially, right?
Is there any evidence that in a normal glucose environment you will have abnormal growth of adipocytes?
Well, so think again. I didn't go into diabetes. That's a different directions that we're now starting. It's not different. It relates. But what happens in diabetes, type 2 diabetes, is that there's no problem with insulin. You know, the insulin is there, but there's insulin resistance, right? So there is glucose that the cells cannot use because they're insulin resistant, and so glucose cannot be consumed, and so glucose accumulates in the blood, and then starts all the complications of hyperglycemia. And at the cell level, that's also a mechanical or a mechanically driven process. And we're very early in that research line, but it clearly connects diabetes and obesity, clearly connect from a biomechanical and mechanobiology point of view, especially with regard to what happens with the plasma membrane.
I'm going to make the same comment that I made yesterday, that the
Can't remember, I had too much wine.
And I didn't hear it, so.
and marbled steak.
Yeah.
That the mechanical situation inside a muscle, or just inside under compression in the seat here, is completely different from the mechanical situation of an adipose tissue that is not under any kind of compression, says the skin tissue or inside the liver.
First of all,
Inside the liver that
there's
you
no
get
such thing
accumulation of fat.
as no compression or no deformation
Yeah,
of
but
the body.
it's
There's
not the
always
same-
gravity, for example.
There's not always gravity.
There's always gravity unless you're living on the moon. But going back to a very simplified cell culture studies,
Gravity is not important for horizontal blood flow, for example. There are a lot of situations where gravity doesn't matter.
well, I disagree. If you put a human being in a zero gravity or close to zero gravity environment, all the cells in the body will be affected. Some are more studied.
Because there is systemic.
For example, with astronauts, what they do with astronauts, they immediately put them, you remember these space shuttles that used to fly? They immediately put them in a wheelchair. Why do they immediately put them in a wheelchair when they go off the shuttle? Because their bodies, especially the bones and the muscles, are so weak. Even after 2 weeks in space, they're so weak that they wouldn't be able to bear their own body load.
Sure.
And you know, muscle and bone is just trivial because people have studied that a lot. But it's much like with these adipocytes. Once you start to look at a specific type of cell or tissue, I'm sure that you will discover that these things apply to other tissues as well. There's no reason in the world why skeleton or skeletal bone muscle would be affected by low gravity and blood vessels wouldn't, right? Especially given the very well characterized mechanical sensitivity of endothelial cells, etc.
One last question, maybe. I was also fascinated. So last summer I was in Sweden for my holidays, and I was really fascinated by the bears, because the bears, they will have a hibernation for about 6 months, because in Sweden the winters last about 6 or 8 months, and when they wake up, and so when you or I would sleep for 6 months, then our muscles are gone, like you as you presented in your talk. However, the bears, they only lose about 10% of their muscle weight during the hibernation, and I think it's really so. The biologist told me about this. The guy told me about it. I was really fascinated by it.
Yeah.
So it's actually not a question, but it's more like
Their
Green water.
physiology is different.
Yeah.
They're adapted to do. We can't fly or swim.
Yeah.
I mean, we can, but not like birds and fish.
Yeah.
And birds can do things that we can't do, and their physiology
Yeah.
is different.
Fascinating.
Could you quickly comment on the modeling aspect, the finite element?
You mean in what terms? The codes, the
No, what kind of model are you treating?
Okay, so at the body level, it's basically reconstruction from MRIs that we export into a segmentation software, which is called Simpleware. And from Simpleware is used to also create the meshes. And then we import it to a software, a free code, which is called FEBio, which is a code that was developed in the States, in Utah, by Jeff Weiss in mechanical engineering there, to specifically solve biomechanical related problems. That's what we do at the macro scale. At the micro scale, we develop our own finite element codes based on segments that we find in the internet, but basically that's MATLAB codes that are used to create stochastically these structures of the cells with the lipid droplets in the nucleus. Stochastically means the sizes and numbers of lipid droplets that we get from the experiments that we're running. So we get variations for each maturation stage of the cell. And then we introduce that as a probability function for the MATLAB code to produce the geometric representation, and then we mesh it, and then it goes again to FEBio for the solution. That's in a nutshell.
Can you say something about the distribution of the droplets of the adipocytes that are very differentiated from fibroblasts into adipocytes, but have got these very, very small droplets? What are the distributions of droplets?
Distribution, you mean in sizes? You can see it here. As the cells mature, and that's not a big surprise, because first of all, they're all very small, so there's not much of distribution. And as the cells mature, you can see that these distributions are growing relatively bigger, but it's not huge differences. These are standard deviations, so there's not huge differences.
And the intracellular vascular membrane around these droplets. How do you characterize that?
No. It's a really nanoscale. Requires, I guess, electron microscopy. We didn't go into that. That's obviously very interesting to do. We didn't do that.
Let's take our meet again. Break maybe for 2 minutes to use the toilets, and then someone wants to